Good afternoon. I'm Peter Housel, one of the members of the OpenDylan project. Today, I'd like to talk about our experiences of generating code for the OpenDylan compiler using the LLVM compiler infrastructure, focusing on implementation techniques, design decisions, and engineering trade-offs. The Dylan programming language is a Lisp dialect that originated in Apple's Advanced Technology Group in the early 1990s. It was initially hoped that Dylan could serve as the systems language for the Apple Newton personal digital assistant, and was later promoted as a development language for desktop Macintosh applications before the project was finally canceled. Other collaborators on the language included Carnegie Mellon University's Gwydion Research Group, who developed and released the Dylan to C compiler, which continued being maintained by our group of open source developers from 1998 through 2011. The third collaborator on the language design was Harlequin Inc., which released Harlequin Dylan as a product in 1998. When Harlequin was split up, the product became Functional Developer by Functional Objects, and then in 2004 it was open sourced and placed into our care. Unlike other Lisp dialects of the time, Dylan was designed to be an applications delivery language. It is a dynamic language, thus the name, at least compared to other applications languages of the time. The language also has features that enable more efficient compiled code, especially library-to-time compilation and the sealing feature. Sealing allows programmers to limit what classes or functions can be extended across libraries so that the compiler can more easily perform type inference, method inlining, and specific method dispatch. This is the basic structure of the Dylan Flow Machine Compiler, DFMC. A reader parses the infix syntax of the language and builds abstract syntax trees. The macro expander expands macro definitions, also operating at the abstract syntax tree level. Modeling and conversion phases turn ASTs into compile time object definitions and the Dylan Flow Machine intermediate code representation. After optimization of the DFM code, 3 pluggable backends can transform it into x86 machine language in the HARP backend, C code in the C backend, or LLVM bitcode in the LLVM backend. This output is then compiled if necessary and linked into a shared library by the system linker. What were our goals in developing the LLVM backend? The first was to support debug information, since the HARP backend only generated Windows debug info. We also wanted to expand support to new platforms such as x86, 64, and 64-bit ARM, ideally without the inefficiencies of compiling via C code. We hope to take advantage of the optimizations that the LLVM compiler infrastructure could provide and support integration with exact garbage collectors such as the memory pool system. All of these goals except the last one have been accomplished. What does the LLVM compiler infrastructure provide? Firstly, it defines an intermediate representation language that allows front-end compilers to represent control and data flow. Secondly, it provides a wide variety of optimizations that can transform LLVM IR independent of the source language. Post-optimization, the LLVM infrastructure can generate machine code for a wide variety of target platforms. There are several possible paths that compiler front ends from the perspective of the LLVM infrastructure can take to generate LLVM IR for code generation. The most popular is to link with the C++ LLVM libraries themselves, making use of their native internal representation. I judged this to require too much cumbersome forward function interface code. Another possibility is to write out LLVM assembly language in its textual source form. This has a greater I/O and generation overhead, and the forward compatibility for LLVM assembly language is often not preserved. I settled on directly generating a compact binary file representation for LLVM IR, known as LLVM bitcode. This has sometimes proved to be a maintenance burden and required reverse engineering the sparsely documented file format, but it has given good forward compatibility. Unlike some compiler-oriented code representations, LLVM IR is explicitly typed. This means that when generating LLVM, we have to supply types for the values we are operating on. Ordinary Dylan tag pointer values are represented using the generic byte pointer type. Operations on tagged integers or characters require a cast operation along with potentially a shift to remove the tag. Dylan heap objects are represented using a single header word, a pointer to a garbage collected wrapper structure, also used to provide concrete type information at runtime, followed by one or more pointer-sized slots. In addition to ordinary object pointer types that belong to the Dylan value type hierarchy, OpenDylan supports a number of raw types for values such as untagged bytes, machine words, and floating point values. These map step straightforwardly to LLVM types. The OpenDylan compiler defines a set of intrinsic primitive functions used in the implementation of the base Dylan library and other low-level libraries to represent operations such as pointer equality, object memory allocation, numeric format conversion, or raw memory access. Depending on the primitive, these are expanded inline by the compiler when they're called, or the compiler inserts a call to an out-of-line version provided by the runtime support library. Here we can see the implementation of the add method on boxed single precision float values in terms of primitive functions operating on raw types. And here's the function as LLVM intermediate code, with two of the primitives expanded inline as LLVM instruction, namely the unbox operation and the floating point add, and the third implemented as a call. Runtime support routines, which include implementations of the primitive functions, helper routines that implement function entry points, and interfaces with system facilities such as the garbage collector or arithmetic trap handling, are generated using a specialized version of the compiler that can generate these routines from a definition like the one shown here. The runtime primitive definer macros build up an LLVM IR function from LLVM instructions, making use of the actual object layouts computed by the compiler. High-level if and loop constructs simplify generated control flow and SSA fee instructions. OpenDylan's implementation of generic multi-method dispatch has a number of different ways of generating code for function calls. When the exact method to be called is known to the compiler, it can either inline the method call or invoke the method's internal entry point directly. Because the exact arity of the called method is known, and any keyword arguments are already split into separate arguments, the call is able to use the LLVM fastcc calling convention, ensuring that as many arguments as possible are passed in registers. The compiler generates an internal entry point for each compiled method. Following the formal arguments, artificial arguments are passed representing the next applicable methods used to implement next method calls, and the method object itself, so the closed-over values stored in the closure objects can be accessed. At the other extreme, generic functions about which nothing is known are called using the external entry point convention. Because the number of arguments that the function will accept is unknown, the caller passes the function object and a count of arguments at the head of the argument list. Since the function arity is not guaranteed to match between the caller and the entry point, because the entry point may need to collect rest arguments or keyword arguments into a stack allocated vector, the looser C calling convention and the C varargs facility are used. When runtime polymorphic method dispatch is known to be required, either at the call site or within the generic function's external entry point, then a decision tree of objects called engine nodes is built. Every engine node has an engine node entry point, also generated as part of the runtime support, most with multiple variants depending on the arity of the methods they are dispatching and the position of the argument being checked. These entry points either implement the dispatch decision themselves or change a Dylan code that performs the discrimination based on an argument value. Once a particular method is chosen by the decision tree, the last engine node chains to it directly when possible, or enters through a method entry point that does keyword argument and rest vector processing. Like Common Lisp, the Dylan language allows functions to return 0 or more values. Most standard calling conventions are not designed to support variable numbers of return values, making this a challenge to support. DFMC solves this with a vector of 64 return values in thread local storage, effectively a large register file. Since most current architecture ABIs support returning a structure of up to 2 words and registers, LLVM functions return the primary value and the return value count as a 2-element structure. Within functions, the LLVM backend works to represent returned values individually as local SSA values wherever possible, rather than going through this thread local storage. Dylan compilers have always included support for foreign function interfacing. OpenDylan's raw types and LLVM's built-in support for C calling conventions make this relatively straightforward. One challenge is code that passes or returns aggregates such as structures or arrays by value. For the most part, the LLVM compiler infrastructure does not support this directly, instead relying on front ends such as Clang, the LLVM C compiler, to know about ABI conventions themselves. Providing platform-specific support for aggregate values in DFMC is an area for future work. The Dylan language supports stack unwinding, non-local exit, and forced cleanups during unwinding with the block construct and its cleanup and exception clauses. The LLVM backend implements these using the Itanium C++ ABI facilities for zero-cost exception handling, which optimizes for the case where the exception is not taken. Function calls within a block that might potentially cause an unwind contain branches to LLVM landing pad blocks that handle the unwind or cleanup. LLVM code generation builds tables that can locate these exception landing pads with the help of a Dylan-specific personality function included in the runtime support routines. In addition to its low overhead in the usual case, this scheme also has the potential to interoperate well with C++ exception handling. The disadvantage, however, is that when non-local exits are frequent, the cost can be quite high, mostly due to the overhead of locating generated unwind tables within the shared object library file using the system dynamic linker. OpenDylan supports module variables that are thread local. In the LLVM backend, these are implemented using the thread local storage model for global variables. This requires that when a new thread is started, thread local variables in all loaded libraries need to be set to their initialization values, and that the storage locations be added to a set of routes known to the garbage collector. Dynamically loading a new library can also cause new thread local storage to be added. At present, this requires that every function that accesses thread local variables check to ensure that the current thread has done all of the necessary initializations. LLVM functions and instructions can be annotated with debugging metadata, translated by the code generator to Dwarf or Microsoft CodeView format. DFMC's LLVM backend can generate this metadata, so the basic source location and local variable information for Dylan programs now works in LLDB, the LLVM project debugger. Work is in progress to integrate the native OpenDylan debugger, which supports breakpoints, stepping, local variable access, and an interactive REPL with a tethered LLDB using remote procedure calls. This is what the debugger and REPL look like on 32-bit Windows using the HARP backend. When the LLDB integration is complete, we will be able to expand the support to Linux and Mac OS. After code generation by the backend, the development environment needs to invoke Clang or other LLVM code generation tools and the system linker to build applications and shared libraries. It needs to support a variety of external tool chains on Windows, Linux, BSD, and Mac OS platforms. Our solution to this is to use an interpreted domain-specific language based on the JAM build system, which was originally a standalone make replacement. Toolchain-specific build scripts provide JAM functions that define build steps and establish dependency relationships between build products, such as object files. When the OpenDylan compiler has finished compiling all libraries needed for a project, it invokes these build script functions to determine the final code generation and linking steps using external build tools. These steps are then executed in parallel as dependencies and CPU resources allow. I hope that this outline of our design decisions and techniques is helpful to other Lisp implementers. We welcome your questions, either here or in any of our community forums. Thank you.